Hello everyone, this is the first video on Newton's laws. So we are going to be covering Newton's first law of motion. An object at rest will remain at rest unless acted on by an unbalanced force. This is the law of inertia. So let's just put that in here. Law of inertia. And so this law of inertia means that an object that is in motion will also remain in motion in a straight line and at a constant velocity unless acted on by an unbalanced force. So this is an important law. This is one of the reasons why an object that is in a low friction zone, like a curling rock on ice, or a billiard ball on a pool table, or any of a variety of options there, even a person walking on ice, can give themselves a little bit of a scoot, and then they can, a little bit of some force, and then they can slide across a low friction area. That's because unless there is an opposing force, i.e. friction, an object will not slow down. So this explains how forces interact as vectors as well. So vectors are always drawn as a straight line with an arrow, and that is because we can always break down even the most complicated of forces into a series of straight line changes. And it also is the law that the result of these interactions and explains the results of these interactions on physical objects. So in the diagram below, we have two forces pushing against a minivan. Both are exerting 10 newtons against the vehicle, but each acts in the direction opposite to the other. We could think about these forces as possibly, this could be friction perhaps on the van, and this could be just a little bit of gas on the pedal, not enough gas going into the engine to actually make it roll forward, just enough to, that first couple of millimeters where you're pushing down on the pedal and the car doesn't actually start to move yet. So at that point, your engine is working. You're putting energy into your engine, and it is doing work. It is putting out a force, but the van itself will not start moving until that force is unequal. If they are balanced forces, then the object will not move. There are also lots of other examples of balanced forces. Right now I'm sitting in a chair, and my weight of my body is pushing down on that chair, but the chair does not collapse. The chair pushes back, holding me up. And it is a case of balanced forces where my body does not move any more or less down. So to determine which direction the van will move, all the forces must be added together. This provides a net force or a total force. So in this case, we have force A, which is, let's call it positive 10 newtons. And we have force B, which is 10 newtons, but because it's moving in the opposite direction, and let's just call this direction the positive direction, we're going to say that it is actually the negative. It is a negative 10 newtons. And since it has a direction, we have to add our vector arrows. So again, we're going to kind of ignore whatever they're doing here, and we're going to say that the force net is equal to force A plus force B, but they must be in the same frame of reference. They must be using the same frame of reference. So that's why force A is positive 10 newtons, while force B is actually negative 10 newtons, because it is moving in the opposite direction. And that can be one of the trickiest parts to keep straight when you're doing these kinds of questions, is which ones are positive, which ones are negative. You need to select a frame. You need to select the direction that's going to be the positive orientation, and then orient all of your vectors in that direction. Okay, the minivan is acted upon by, in this case, these two forces. If you add positive 10 newtons to negative 10 newtons, then your total will be 0 newtons. So this is a balanced system. Now let's think about some applications of Newton's first law. Did you ever go rollerblading and hit a rock? Rollerblading, skateboarding, biking, any of these sort of activities. And if you hit a rock, then something usually happens. So I'm gonna do a doodle. I like skateboards because they're easier to draw. So I'm gonna put a little skateboard here. Here's my little guy. Or girl, whatever. Skateboarding's for everyone. And let's put a little helmet on in case somebody's watching this, in case my kids are watching this video someday. Okay, so he's got his little helmet on, and there's a rock here. And so as my skateboarder comes along and hits the rock, they have both, before the skateboarder hits the rock, let's just draw him back here. At this point, the skateboarder is actually moving and he's gliding along. He has a velocity, but in fact there's no force being acted upon the skateboarder if he's got both feet on the board, except for a little bit of friction, right? So there is a little bit of friction. And otherwise, so he will slow down a little bit, but if it's got nice oiled up bearings, then we can probably even ignore the friction for a bit. And he's just gliding along. And in fact, he is in a state of inertia. He is moving. He'll be moving at a uniform speed if we ignore inertia. And so if we're just gonna, let's just cancel out. Let's ignore. Okay, ignore the inertia. And then he's moving at this constant speed. And then here's this rock, right? So I'm gonna leave my guy here. I'm gonna duplicate him. Now when he hits the rock, what happens is that all of a sudden the rock exerts an unbalanced force. The rock exerts a force on the skateboarder in the reverse direction, and the skateboard stops moving. Now, unfortunately, for the person riding the skateboard, they do not have the force, and so they continue to move at a uniform speed. And so in this case, they're both moving at the uniform speed. Now, here, the rock stops motion of board, and the rider continues to move at uniform speed. Unless they're a better rider than I am, and they jump off of it or they put their foot down. But one way or the other, they're going to feel a difference. If you are in a car and you rear end somebody, or if you hit something in a car, the thing you're going to notice is your face is going to go forward and hit the steering wheel, or hopefully you have airbags which are going to provide some pressure to stop that from happening. So this other question, what are headrests for? Well, in the car, the headrest is there because after hitting the airbag, your head will move backwards, and actually no, wait, is it well, and you can also imagine that the headrests are there because you don't really have a force pushing directly on your head when you start your car, and so the headrest supports your head as the car accelerates forward. Okay, so let's just put something down here. The headrests support the head as the car accelerates, so that the force acting on the car also acts on the head. Otherwise, the car would move and the neck would snap backwards. Otherwise, the car would move and the head would stay in place, hurting your neck. And we can do a little, one of the things you'll notice about physics is that they really benefit from being able to doodle. So I'm going to put that over here. I'm going to put this one up here. I'm going to get a little doodle here. So here is your person sitting in the car. So if you have a chair like this with the head up here and the person's arms are on the steering wheel, then as the car goes forward, when the car goes forward, when the engine goes, engine force, it will move the car forward, but the head has no force. So if we duplicate this, it will very quickly be a case where the head stays here and the car moves forward. And then their person's neck is going to go like this. Ugh. And then sore neck. If we replace this with if we put the headrest on, then this force that the car is exerting is also acting on the head. So also acts force on head. So the head is supported as the car accelerates. So those, this wasn't a problem in the early designs of cars. Lots of early 40s cars didn't have headrests, but also those cars couldn't accelerate at the rates that our cars can today. They're also there to support the head in a car collision where the head snaps backwards. So unequal forces is the other concept here, and that's sort of a concept we kind of are covering already. When forces are unbalanced, that means there is a greater force in one direction than in another. When there are unbalanced forces acting on an object, this will cause the object to move in the direction of the stronger force. The minivan below is acted upon by unbalanced forces and consequently moves in the direction of force A, the stronger force. So force A is a positive 10 newtons. Force B is a negative 5 newtons. So when we do the forces together, we get 10 newtons plus negative 5 newtons, which leaves us with a positive 5 newtons of force. So that's 5 newtons to the right. And so the car will now start to accelerate because force is proportional to acceleration, mixed in with a dependence on mass. All right, with that said, I'm going to also link up a couple of videos that show you some examples of Newton's first law and possibly some activities, and that'll be it for today. And we'll talk to you tomorrow about Newton's second law. Thanks, everybody.